Hello everyone, I'm Dirk Helbing. I hope every one of you has come well through the COVID-19 times, very crazy times we've never seen before. But with your help, we may make a contribution to mastering the challenges we face. I wanted to talk today about opportunities and pitfalls of data science. And of course, everyone knows that we are living in a time of big data. Within just a minute, 700,000 Google queries are being sent, 170 million emails are being sent, and a lot more data is being collected, GPS location data, and all sorts of other data. So this basically has created this big data dream that Chris Anderson has formulated like this. It would be an end of theory. The data deluge would make the scientific method obsolete. Well, is it really like this? We'll have to see. For some time at least, the hope was that we could now know everything, that we could understand the human body, brain, and personality, and people said data is the new oil. So then, what is the new motor, we could ask? And people say, well, that's actually artificial intelligence. Artificial intelligence, of course, has had a phenomenal success story recently. It's on the rise exponentially or even faster. It's getting ever more powerful, and people are using it in order to make sense of big data, and they want to see what is wrong and where the system is broken in order to fix it. And in fact, there are some success stories of data analytics and machine learning in medicine in particular, and this includes, for example, the diagnosis of cancer. It seems like machine learning can actually diagnose cancer more reliably than many doctors, some cancers at least, and that of course is a fantastic and very useful application, and could save a lot of patients. In science, of course, we're interested in how science actually works, and we've been looking into the brain trace of notable people over thousands of years. It turns out that even based on birth-death data, one can actually reveal a lot of the history of arts and science. And today, of course, we have a lot more data. We have publication data, we have citation data, we have network data, and so that actually reveals a lot more things, including, by the way, the spreading of ideas or memes, as some people say. This is for the case of physics, and as you can see over here, it gives a pretty clear picture of what were the hot topics at a certain point in time. I'm not sure who of you is a physicist. I am. So, Kondo effect, for example, photo emission, we see quantum wells, Hubbard model, quantum Hall effect, Bose-Einstein, neutrino, quarks, carbon nanotubes, and entanglement, graphene. I was actually pretty impressed about this clear picture, because when I studied physics, there were a lot of things going on, and the picture wasn't that clear. So data analytics can help us actually to look into these things. It can also help us to get a better picture of violence and conflict and what we can do to counter it. We've been looking, for example, into data of conflicts in Jerusalem. We used it in order to set up agent-based models that were calibrated and validated and allowed us to look into alternative political scenarios, and also that work got quite a bit of attention and recognition. Now, on the other hand, here's the challenge, right? Let's go back to COVID-19, and if we're trying to fit curves to confirmed cases, of infections, and basically, it turns out that it's not that easy. That's something that probably you've also seen in the past weeks and months, where sometimes you may have been at the top of the list and then again somebody else has overtaken, and it turns out to be a pretty tricky thing. Have a look at the blue curve over here. It turns out that, for example, the logistic curve is largely overestimating real cases. And that is something which is consistently so. The same thing for the percentage of cars that have been predicted in a society, and for many other application examples. The whole thing has to do with the point that, of course, your fit model contains parameters. Those parameters need to be estimated, but you will not get an exact value. Instead, you will get confidence intervals. And the real parameter could be any parameter in that confidence interval. So if you simulate the model with different parameters in the confidence interval, you will get a large spread of predictions, as you can see over here. So in many cases, actually, predictions can be far off the real development, and that can be pretty frustrating. The reason, of course, is that the data that you need in order to identify saturation effects and also turning points and later declines, this data comes up not in the beginning, but at a later point in time. So in the beginning, you cannot do an accurate prediction reliably. This even applies to predictions of the world population, or take the prediction of oil production, peak oil predictions. That is really very important for our entire economy. While predictions back from the year 2008-9 predicted that we would already have passed the point of peak oil. And of course that hasn't happened really. If you look into new predictions, and basically there's a large spread of what would actually happen. And the same applies even to oil consumption, oil price, and of course also global warming. I realize that, of course, the scenario that we would see very much depends on what we do in order to counter global warming, but that's not the only problem. If you go back into these curves between 1900 and 2000, you see also that these curves don't fall on top of each other accurately. So in fact, there's also some uncertainty in terms of what would really happen. The question is, will big data solve these problems, right? And then of course we would think of Google. They have a lot of data, and they've also tried to predict the flu. And Google Flu Trends, in fact, was one of the great examples, success stories, in fact, of big data analytics in the beginning. However, if you now visit the page, then it turns out that they have closed down Google Flu Trends. And the reason is that, in fact, it didn't work so well. Partly also because they're now making suggestions for searches. So they're influencing people, and that's disturbing the measurement process. But not only. Unfortunately, this magic formula that more data is more knowledge, and more knowledge is more power, and more power is more success, that doesn't always work. Do we even know how to refine raw data, to distill it into useful information, into knowledge and wisdom? Well, that is much more difficult than one would think. Just take a lot of data points. How are they connected? What did they really tell us? And so it turns out that, of course, you could connect these data points in different ways. That's, of course, only a funny example. to make the point, but in reality we do have the problem of overfitting. So if you want to have a good picture of a city, should we represent the city in 3D? Should we represent it in 2D? With all the trees and bushes in there, or is it still too much information? Shouldn't we simplify it? And that is actually what we do if we're using maps. We don't want to be distracted by all the details. We don't want to have the problem that we don't see the forest for the trees. So we really need to take care that we don't use models with too many parameters. It's quite a challenge to figure out how detailed should the model be. And of course that very much depends on how much data do you have. What kind of model do you have? And there could be even this problem of spurious correlations, right? The more data points you have, the more patterns would be in the data just by coincidence. Take this example. Number of serial killers as a function of chocolate consumption, If that was a causal relationship, then it would be very dangerous to live in Switzerland, indeed. Fortunately, it's not. But we really have to pay attention that we don't make the mistakes to see patterns where they actually are not meaningful. It turns out that it has happened many times. So, of course, we love to use machine learning, but not always does it give us very useful results. And partly because correlation doesn't mean causation, right? It could be that A causes B, it could be that B causes A, it could be that a third factor C causes A and B, or A and B could just appear to be correlated. A fun example is this one. So, number of forest fires is strongly correlated with the number of ice cream eating children, right? Because it's outside heat that determines both. Now, if you would lock children into their rooms, or if you would forbid them to eat ice cream, of course that wouldn't reduce the number of forest fires at all. Now, if you think these kind of wrong conclusions from data wouldn't happen in reality, then unfortunately you're wrong. There have been many examples also in medicine where there has been overfitting and there have been misclassification. So there will be classification errors no matter how much data you have. There will be false positives and alarms that don't go off. And that is actually a quite common thing, not only in cancer screening. That's one of the reasons why it is often not so reasonable to apply a certain kind of diagnostic methods to an entire population, because there would be many false alarms and there would be action taken, and not necessarily would that action taken be good and could produce a lot of unintended side effects and harm. We take predictive policing, for example, then the error rate can be quite massive. In many cases, it's actually above 90% or even 99% when it comes to flight passengers, for example. It takes 40 people in Germany to sort out all the false alarms. So that is quite concerning. For every real terrorist, there would be 100,000 false positives. And it would be even more concerning if there was a machine bias, if algorithms would discriminate against certain kind of people. So we need to be careful. How are we using data and machine learning? And also the issue is that machine learning wouldn't always converge, right? In the following example, we're trying to fit an infinity sign, but we will increase noise in the course of time, and noise of course is always in the data, so you will actually see that there will be a lot of misclassification. The patterns that we produce could be pretty wrong. And sometimes even the machine learning algorithm may not converge because some systems are scale-free, and that is actually posing quite a bit of a challenge. And then as a result, you may read headlines such as Dr. Watson failed, or think twice before you're consulting Dr. Google, because yes, things can go wrong, and we have to be aware of this, even though of course data and machine learning can have a lot of positive applications for us. But as I said, we would want to be careful. We want to have understandable tools and explainable results, and that's why today we're not just doing big data analytics, we're using data science. And data science brings together data with machine learning, with statistics, with domain knowledge. And that would often give us better insights and results. I'd like to end my talk by referring you to a publication that Dirk Brockman and I had in Science a couple of years back. Here we have been looking into epidemic spreading data. So assume we have a globe, and whenever somebody catches a certain disease, there would be a point flashing up on this globe. So we would have this spatial temporal infection data. Now, if you would look into this data, we would be very frustrated because we would get very poor correlations, very widely scattered data clouds. And the reason is that actually times have changed since the times of Black Death, when basically this disease has spread based on diffusion, because people have not moved much between places. In the meantime, of course, that diffusion pattern has been replaced by a pattern where people would use planes, and as a result, the spreading patterns would look pretty much different. However, if we take into account passenger data and use it in order to define a new effective distance, then we could actually see a circular spreading pattern among cities within this effective distance representation. It would allow us to determine where disease originated, but it would also allow us to take proactive measures to put medicine and medical personnel in place in those cities that would be hit next in a global pandemics. And now you can see there is a strong correlation. We have a much better picture of what is going on. We can understand the dynamics, we can use it for prediction. And so this is now for COVID-19, results by Dirk Brockman, and we know of course that the entire thing started off in Wuhan, in China, and then basically it moved on to Europe and to the United States and South America, so it didn't happen all at the same time. If we put that now into this effective distance representation, then you would find this circular spreading pattern over here. And there's also another presentation that's often being used. So this again is Wuhan in China, and then it takes time for the disease to spread to other cities. We could make an approximate prediction of when what city would actually be hit and prepare accordingly. So actually science can do something to understand what is going on and why. And so we're hopefully finding our way through the pandemics with the help of science and with your help. Thank you very much.